Okay, today we'll be talking about the principle of superposition. This is kind of an interesting topic, actually. Can your head and your friend's head occupy the same space at the same time? Well, obviously not, because they're solid objects, but waves can. Interference is when two or more waves occupy the same space at the same time. Waves can do this, but solid objects cannot. We know that two objects cannot occupy the same space at the same time, but waves can. And the question is why? And the answer is waves are only energy. So two or more waves can occupy the same space at the same time because really all you're doing is having energy at the same spot, or more energy or less energy at the same spot. This leads to what's called the principle of superposition. When two or more waves are traveling through the same medium, the resultant wave is the sum of the displacements of the individual waves at each point. And there's two basic types of interference: constructive and destructive, and we'll look at each of those individually. The principle of superposition assumes small amplitudes. It works for all types of waves. For example, it works for sound waves with like music. You can hear all different types of instruments interfering with each other. Electromagnetic waves like light and radio waves. And since it works for electromagnetic waves, obviously it must not require a medium either. Okay. Constructive interference is when two waves add in the same direction. So let's look at this, sending two pulses along this rope. It happens first at A, and then B, then C, then D. So A has this crest coming towards this crest. You can see they start to interfere here. They totally have constructive interference when they're exactly one on top of each other. And then they continue on their merry way as if they weren't even interfering with each other. Okay, so it doesn't destroy them, they just keep on going as if the other one wasn't there. Okay. Constructive interference, two or more waves combine to form a larger wave. So here we have two waves. We have wave 1 and wave 2. Wave 1 has an amplitude of 2, and wave 2 has an amplitude of 1. So here's wave 1, has an amplitude going up 2 units and down 2 units, so therefore has an amplitude of 2. This one has an amplitude of 1. What would the result of constructive interference look like? So in other words, when these two waves are exactly lined up with each other, okay, or in phase, what would it look like? It would look just like this. 1 plus 2 is 3. All right. Now how about destructive interference? Destructive interference is when displacement overlaps, when they have opposite signs and momentarily cancel each other. So here we have the same idea of the two pulses coming towards each other, but now one's a crest and one's a trough. They come towards each other here. They start to overlap. They cancel each other. Now obviously they don't totally cancel each other because this crest was higher than this trough. And then they continue on their merry way as if the other one wasn't there. When two waves always meet condensation to condensation and rarefaction to rarefaction, they are said to be exactly in phase and exhibit constructive interference. So let's say you have two speakers set up and they're making condensations and rarefactions, and they're both in phase, so they're both giving out the same signal at the same time. And where two condensations or two refractions meet, they constructively interfere with each other. And that would look like this. You have the two of them here, completely in phase. They line up with each other. Right? Okay, so how about if they don't line up condensation to condensation or rarefaction to rarefaction, but they're exactly out of phase? In other words, we have a condensation hitting into a rarefaction. What would happen? And what we did here is we have the same setup, but we actually moved this speaker back a half a meter. Since the wavelength is a meter, moving it back a half a meter ends up having the situation where a rarefaction meets with a condensation, and we end up getting this situation where we have an amplitude going up and an amplitude going down, and up and down. The two of them end up canceling each other out, and that would be completely destructive interference. This could be seen in the noise canceling headphones. It's really kind of cool what happens. Is sound comes in, and obviously it could be playing music or what have you, or it could just be to deaden sound as well. But what it does is it takes the noise on the outside, it picks it up, and it inverts it 180 degrees out of phase. So what ends up happening is it ends up taking that same outside noise and it reproduces it, but exactly out of phase. So this ends up being completely destructive interference. So the two waves are out of phase. So like here where there's a crest, there's a trough here. And it ends up canceling the noise. So it's kind of interesting when you think about it. By playing noise out of phase with the incoming noise, it cancels it because of completely destructive interference. Two overlapping waves with slightly different frequencies give rise to the phenomena of beats. All right, so here you have two tuning forks, and they're off by 2 hertz. And the reason they're off by 2 hertz is they put a little piece of putty on one, so it changed the frequency of it ever so slightly. So they end up reinforcing each other, but in a very interesting fashion, which you'll see in the next slide. So what happens is, once in a while, they completely line up with each other, and once in a while, they completely cancel each other, like right here at 5, where this one is a crest, that one's a trough, so the sound almost completely cancels each other out. But here at like 2.5, they're both troughs, so they reinforce each other. So it goes from a situation where it gets really loud to faint to really loud to faint.